So the cool thing, and one of the many cool things actually, about the periodic table is that we can actually use it to find the electron configuration for all the elements. And it basically has the order within it, so we don't need to remember the order. It's basically there for us to use. So I'll show you what I mean. For example, if we want to find the electron configuration for oxygen right over here, and it has 8 electrons, so we need to find the electron configuration. So the periodic table has been divided in a special way, where these two columns over here, these two periods, are in the S sublevel, and this block over here is in the P sublevel, suborbitals, and this transition metals over here are in the D sublevel, suborbital, and the lanthanides and actinides are in the F suborbital. But make sure that, I know it's like the lanthanides and the actinides, but actually we disclude the lanthanide and the actinide, lithium or whatever the element is called, this one, La and Ac, from the F orbital. It's actually included in the D orbital, but D suborbital. But starting from the elements after La and Ac, those are in the F orbital. So, okay, let's try to do the oxygen electron configuration. So it tells us the order of how it goes. You know how sometimes you can instead of using a periodic table, you can use this method, like the arrow thing, where you write all of them, and then, you know, this really annoying kind of thing where it might get really messy and stuff. And yeah, so instead of using that, we're going to use this way. So the first thing, the first sublevel that we can fill, and the amount of electrons we can fill it with, is, we just look at the periodic table. It's so magical and so nice. Okay, we would look at, 1s. Okay, so we'd look at the first energy level. The energy level here is the period, basically. And the period here is 1, so that means our energy level is 1. So we write 1, big 1. And then our sublevel suborbitals is an S. So we write S. And how many electrons can we fill our S with? And it's, as there's 2 columns, that means we can fill our S orbitals with 2. And as we are not hydrogen and we only have 1 electron, we have more than 1, and we actually have more than 2. So we're going to fill the whole sub-level of S, and by putting a small 2 on there. So the next suborbital we would have to do is just move along in the periodic table. And as we move along in the periodic table, so we filled in 1s1 and filled in 1s2, and then you move to the next thing in the periodic table, which is energy level number 2. There you go. And then as oxygen is over here, so we're going to fill the whole thing, you know, because oxygen ends with being in the P suborbital. So we have to fill this up again, and as it's in S, because it's in this block, and S can be filled up with 2 electrons only, because there's only two columns, what is it called? 2 periods. Yeah, okay. And then after we're done with that, we move on. Oh, there we go. It's still in the second row. That means it's still in the second energy level, but we are in the sublevel P. So we put P, but we are not going to completely fill this sublevel of P, because as you can see, oxygen just stays over here. It's not at the end of the sublevel. It's not completely filled. So how many electrons are going to be put into P because of the amount of electrons in oxygen. So we are going to be 1 electron, 2 electrons, 3 electrons, 4 electrons. 4 electrons of oxygen are in the P suborbital. So that is our electron configuration right there. It's really, 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 really easy. Okay? And so yeah, let's just try another example. But here's another trick that you need to learn rather than this. That when we reach this part here, the transitional metals, when we reach the transitional metals, the rules are a bit different. That, for example, this here, or this one right here, the energy level is not 4D. It's not 4D. As you can see, it's actually 3D. So the energy level of these D blocks is basically the energy level on -1. So it's energy level -1 is for the D. Okay, so here it's 4, but then you would -1 and it'll be 3D. And same thing that goes to the F suborbitals. There's actually another rule. It's not -1 this time, it's actually -2 for these ones right here. So if it's actually 6, we would -2, and that means that the energy level starts at 4F for these elements right here. So we need to remember that when we're doing the electron configuration. So let's try Ti, okay? Oh, and another thing that really comes in handy as you go down the periodic table, you know, you're gonna have to add a lot of suborbitals and a lot of energy levels, and the electron configuration is going to be really long and really tiresome to write, and you don't want to do that. So a trick you can do is called the shorthand electron configuration, and it's by using the noble gases, because the noble gases have you know, they have filled suborbitals, filled d suborbitals, and filled the s orbital. So we're going to use it. Like, for example, let's try finding the electron configuration for a Ti. So let's, you know, use the shorthand way. So we would look at the electron configuration, the noble gas before the Ti. So it's this way. It's right there. Before it, not after it, before. Okay, so this one right here, and that one right there is AR. So this here is actually AR. So we're going to do this. We're going to write AR in these square brackets, and then we're going to carry on writing the electron configuration after AR. So this basically means that we wrote the entire electron configuration for AR, and we're going to carry on. So instead of writing the whole entire thing, we're just saying, as if we wrote all of it, now carry on. Okay, what's different from AR for Ti? Okay, so we'd have to write the difference between them, which is, we'd go here, and then we'd go, okay, energy level 4, and then it's the sub level S, and then we're going to fill the entire thing, and we can fill it with 2, and then we'd move on here. Oh, there we go. The tricky step. It's not energy level 4, it's energy level 3 with -1, remember? And then it is the D group now. So now it's D. And how many electrons are we going to fill in the D? We're not going to fill the whole entire thing with 10. Ti is not over here, it's over here. So that means we're going to fill the D level with 1, 2 electrons. And that is our electron configuration for Ti. It's pretty simple, right? And you do the same thing for this one, and that's basically how you can do it really quickly. And a really important thing to remember is that when you write the electron configuration for the transitional metals, you can find the amount of valence electrons it has. And I will show you how you will do that. Because you know how sometimes you actually need to find the valence electrons for transitional metals or for other elements to do something, for example, like drawing the Lewis structures. And the transitional metals are kind of hard to find the valence electrons, as easily as trying to find the valence electrons for oxygen. So to find that out, we would use the electron configuration of the transition metal or whatever element you want, and by doing whatever I'm going to tell you right now. So we know that oxygen has 6 valence electrons, right? Because it's like 1 valence electrons, 2 valence electrons, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, 8 valence electrons. Yay! Okay, so we know that, but let me just show you how you'd be able to find that out using the electron configuration of oxygen. And it's pretty simple. So you would look at the electron configuration, and you would look at the biggest large number, which is the highest energy level. And the highest energy level that we actually have is the 2, right? So after you find the 2's, the largest number, the highest large number, okay, which is 2 here, you would add the small numbers that are connected to the large number, which is 2 and 4. 2 plus 4 equals 6. That looks right, right? 6 is the amount of valence electrons for oxygen. So you can do the exact same thing for a transitional metal, but when you're trying to find the valence electrons for an element, you can't do the shorthand way. You can't. To spare any mistakes, you have to write the whole entire electron configuration, and then from there you would have to find the largest energy level, which is the largest big number, the highest big number that you have, and then you have to add all the small numbers for that largest big number that you have. And then that is your amount of valence electrons that you have for that element. It's pretty simple. So now we're going to move on, and I'm going to explain some principles and rules. So we have Heisenberg's uncertainty principle, and he says that you can't determine the position and the momentum, and momentum is basically mass times velocity, of an electron at the same time. Like if you find one, you can't really find the other. Or if you think you found this one, the certainty of this one would be more than the certainty of the momentum. So your certainty of the momentum would be less than your certainty of the position. If you found the position, you wouldn't really find the precise momentum, or the other way around. Why is that? Because, for example, if you're trying to find the position, and when people are trying to find the position of an electron, they shoot an incident photon, and then it hits the electron, and the scattered photon tells them what position, and so on. But when they do that, when they find the position of the electron, they actually ruin the momentum of the electron, because they hit the electron, and the electron moves, and its velocity changes, and its direction changes. And velocity is an important part of finding the momentum. So that's Heisenberg's uncertainty principle. Moving on to Aufbau's rule. Aufbau's rule makes a lot of sense. Is that you would fill in the electrons from the least energy level, energy sublevels, to increasing energy sublevels. And if we go back to the periodic table, first energy level is 1s, and then 2s, and then 2p, and then 3s, and then 3p. But then it's not 3d, as you can see, it's actually 4s. So if we go back to the periodic table, see, it's 2p, 3s, and then it is, wait, what did it say? Let's go back. Where was it? Okay, 2p, 3s, 3p, 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 and then 4s. See, it's 3p and then 4s and then 3d. So that's an increasing energy sublevels. So yeah, it has a specific pattern. It's not increasing energy level number, it's increasing energy sublevels. Yeah, it makes pretty much sense. You fill them in order. You'd fill this one in before you filled that one in. I mean, you wouldn't do this and then you would do this. I mean, you'd go in order. It makes a lot of sense. And then there's another rule, which is Hund's rule. And Hund's rule is pretty funny, actually. I don't know. Is that Hund's rule is basically that electrons prefer their own orbitals. Like, to remember that, I like to think of, Hund's rule, and I change the word into hunt, because, like, electrons hunt for their own orbitals. It's funny, but, like, silly or whatever, but it makes you remember it. So, not mix up with Aufbau's rule. So, yeah, it actually hunts for its own orbital. It likes to be alone. They're all selfish and everything. And they prefer to have more parallel spins. So they try to, move around and try to make it that they have more parallel spins. They like that. So that's Hund's rule. And sometimes when we're trying to apply Aufbau's and Hund's rule, things don't go so well, so we kind of get some exceptions. For example, let's look at an exception of chromium, whatever, I forgot the name, CR. And the electron configuration, the shorthand one is AR, and then for S1, 3D5. And you're like, hey, that doesn't make any sense. Why did the S1 only fill up to 1 and then they moved on to the next suborbital? Why did they do that? That's totally against Aufbau's law. They didn't finish this sub-level and they moved on to the next before finishing this one. Why did that happen? Well, sometimes when you're trying to do both rules together, the other one kind of wins. Like the Hund's rule. So basically what ended up happening is that this is how CR actually is because of Hund's rule. They didn't fill this one up. It didn't end up looking like this, It ended up looking like this because they wanted to have more parallel spins. They wanted to have more parallel spins, and this one's actually kind of empty. It doesn't look that great. I don't know. But yeah, so sometimes there are exceptions to the rules, and that is all you need to know.